The great advantage of string theory is that string theory apparently is a single theory. There's only one string theory. There are no parameters. It's just what it is. All you have to do is figure out its consequences. Sadly, the consequences seem to be to generate an enormous number of universes, all of which have different properties. And so the dream of a while ago, which was to predict the properties of our universe from first principles, seems to be impossible.
Hello, this is Robinson Erhardt here with the introduction to Robinson's podcast number 173. And this episode is with Ken Olum, who is research professor in the Department of Physics and Astronomy at Tufts University, where he works on exotic physics and topics in cosmology like cosmic strings, gravitational waves, anthropic reasoning, inflation, and time travel, all of which, except really for cosmic strings, have been covered in at least some capacity on the show. So then, as you might imagine, though you'll already know this if you've clicked on a link to find this, that this episode is about cosmic strings. And there are quite a variety of them, as you'll hear. Though I should really say there are conjectured to be quite a variety of them, since their existence is yet to be confirmed. But in general, cosmic strings are stringy, nearly one-dimensional astronomical objects of astronomical proportions, at least in that one dimension, that move very fast and are very massive, and that may have been created in the early history of the universe. And our conversation starts out just a little bit slowly, I think, but the material quickly becomes super fascinating. And beyond cosmic strings, we also talk a bit about string theory and the multiverse. And string theory is not necessarily connected to cosmic strings, though there are string theoretic cosmic strings as well. You will have noticed, maybe you've heard the last episode, but seen the last episode on YouTube, or I guess listened to it, but I've got a new t-shirt today. It says Geesling on it, and it's for those OG Geeslings in the know. Likes, comments, reviews, subscribes, please. Love those. Always help. And now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Ken. I've identified a trend in your research in that it seems to center around novel or exotic areas of astrophysics and cosmology. So black holes, cosmic strings, time travel, the multiverse, and so on. And I was just wondering if this is what you've always been interested in, like even before going into physics professionally, were these the topics that stood out to you?
Yeah, I think so. When I went into physics, I said I wanted to study fundamental things. What's the universe made of? What are the, how did the universe begin? What are the fundamental laws of physics? And so that attracted me to particle physics and cosmology.
But I guess what motivates it? So you mentioned the most fundamental things. Why are you more interested in the, at least as far as your research is concerned, in the exotic rather than perhaps the merely tiniest or most fundamental microscopic constituents of the universe? Or maybe all these topics, are related in some way.
Yeah. So I don't think I'm the person who wants to say, the regular ideas of physics are wrong and should be replaced with more exotic ones. I'm be happy to study the smallest things, the most fundamental things. But it always becomes exotic. We have the standard model, so that's good. And now we would like to know where the standard model comes from. So that's some kind of new physics. So how are we going to find out that new physics? Well, by studying things which are on the borders of what we understand.
Mm. Well, that makes sense. So I did an episode a few months ago. I already can't remember if this was in May or June on the NANOGrav data release. But since it's been a long time now, and for new listeners also, could we just run through what a pulsar timing array is and just what NANOGrav discovered evidence for earlier this year, or announced their discovery of earlier this year?
So we do precision timing of pulsars. We at NANOGrav timed 68 pulsars and use them to look for gravitational waves. So the important property of a pulsar here is that it emits pulses rapidly, like every few milliseconds, and very regularly, so that you can look at the pulses. They're coming in a steady stream. You can come back a month later. You can say, oh, look, these pulses are delayed by 100 nanoseconds from the pulses that I saw a month ago. Why is that? Well, could be gravitational waves, could be many other things too. It's a pulsar timing array because we time a whole array of pulsars, and we look for correlations between the timings that we get from the different pulsars to see that they're correlated in a certain way that might be indicative of a gravitational wave.
So what is the more well, I mean that is what NANOGrav has been doing, but then what did NANOGrav just announce the discovery of?
So we have strong evidence for a background of gravitational waves at very low frequencies. So we're talking about waves with periods of years. We announced it in a series of coordinated papers right at the end of June. This is the first discovery of a gravitational wave background. So gravitational waves were observed starting in 2015 by LIGO and then Virgo and Kygra. But these were bursts, events, bursts of gravitational waves coming from colliding black holes or neutron stars. What we have this evidence for is a background, meaning there's lots and lots of sources. We don't know what they are. The simplest explanation would be supermassive black holes with masses of 1 billion solar masses orbiting each other at the centers of galaxies. And what makes a background is that you have lots of these sources. So they're all radiating from all different directions. So it's like you're in a big room and there's a lot of people talking and you can't hear what anybody is saying, but you can hear that there's noise. So you can say, well, I hear a background noise. A lot of people are talking at once here. So maybe a lot of black holes, or it could be cosmic strings, could be many other things, all radiating at once, and they merge together into a background. So it's the first detection of the background, and it's what one could say is sort of the second observation of gravitational waves. Of course, LIGO and the other interferometers found many, many individual events, but this is a very different type of detection. It's a very different frequency, periods of years rather than a fraction of a second, and a background rather than individual events.
And so the more conventional, or perhaps most likely, and tell me if you think these qualifiers are wrong, explanation for the data, or at least some of it, if that's how you'd prefer to look at it, is supermassive black holes?
Simply because we know that galaxies have supermassive black holes. Every large galaxy that we've been able to check has a supermassive black hole at its center, and we know that galaxies merge. We can see them doing it. And so that gives you a galaxy with 2 supermassive black holes. So it stands to reason those are going to fall down to the center of the galaxy, eventually get in orbit around each other and produce gravitational waves. So in terms of the data, it's not that the data is a better fit for supermassive black holes than, say, cosmic superstrings. Any of those are possible explanations. It's just that when you see something, you're trying to explain it, the first thing to think about is something that you know exists, rather than some speculative thing that may or may not be present.
And I'd like to get back to the strings in a moment, but first, with regard to the supermassive black holes and the galaxy mergers, is the reason that there would be sufficient density of these entities merging in throughout the universe to create a background? Is this because maybe one, there is just such a pun intended, an astronomical number of these events happening at any given time, but also that the mergers last for a sufficiently long period?
So it takes a long time, depends on the mass of the black holes, but thousands of years, million years, for these black holes to orbit around each other faster and faster, spiraling in. Eventually they get to a frequency too high for us to detect. Eventually they merge with each other. The mergers are quite rare, but there are a lot of black holes which are currently orbiting. Maybe, we don't know, but it's believable. Estimates of this show a fair number, not millions, but tens, hundreds of black holes not too far away, close enough that they make a significant contribution to the signal. And they do it for a long time before they eventually spiral in and hit each other.
Would you expect that, given the less fine-grainedness of the black holes, that if you were to compare the gravitational wave background to the cosmic microwave background, you would expect to find even more anisotropy in the gravitational wave background?
Right. Anisotropy is very important. We don't have the data yet to be able to detect it. We can set some bounds, but they're very weak. But this is very important. There's anisotropy both because the structure of the universe around us is not completely uniform, more galaxies in some places than others, but also because there are only a few, especially if you look at particular frequency ranges. So every pair of black holes is emitting like a single tone. It's emitting at one frequency. Changes with time, but at any given time, it's emitting at one frequency. So if you look at a range of frequencies, there's not going to be that many. So if there are 10, they're not going to be exactly carefully spaced around us. More likely, one is brighter than the others. It's off in some direction. Eventually, we hope to detect the individual pairs of black holes. But probably before that, it's not completely clear. Possibly before that, we're just going to see more signal coming from some direction, because it happens that of the 10 black holes, 3 of them are over in that direction, and they're kind of concentrated, and so they make a sort of a bright spot.
And then when you say that we don't have the data for this yet, is that because we just simply don't have enough binary pairs of pulsars, so PTAs, to really map out the sky as fine-grainedly as we would like?
We need more pulsars. We need a longer time of observation. So just doing nothing except taking data for another 5 years will improve our ability to do things. We also need better data analysis. So, when I say this to try to explain how pulsar timing works, I always start by saying, pulsars are these super accurate clocks. And they tick very regularly, and we can observe any distortion in the regular ticking. But that is kind of an exaggeration because, in fact, there are lots of irregularities. There are intrinsic irregularities in the spin of the pulsar. There are propagation delays. These pulses have to go through the interstellar medium to reach us. Sometimes they go a little faster. Sometimes they go a little slower. And so just more work, better understanding of all those phenomena might help us to process even the existing data and get some better information out of it.
And am I right that you are you focus much more on the data analysis side than the collection. Mm-hmm. Well, the last thing that I'll ask about this before we move on to some of the more exotic phenomena is just what is the mechanism that in a supermassive black hole merger produces the gravitational waves that we're getting evidence for from the PTAs?
Well, anything which is massive and which is accelerating produces gravitational waves. So, if you wave your hand around, you're producing gravitational waves, but they're extremely weak. You aren't able to detect them. So what you need is something very, very massive, like a black hole, which is accelerating. Well, what's going to make it accelerate? Well, this is a huge, massive thing. It's very hard to move. So what's going to make it accelerate is the gravitational force due to another big black hole. That's why we want pairs of them. The pairs of them are always in acceleration around each other as they orbit, and that produces a steady stream of gravitational waves.
So, as you've already indicated, we have the data, but it's just that supermassive black holes, because we know that they exist, are the most likely source of them. But this doesn't rule out other more exotic possibilities. And maybe before getting into how the data might show this, because cosmic strings have never come up on the show in 200 episodes, maybe we should spend some time going into just what cosmic strings are.
All right. So if I would say to you cosmic string, and you would think, what the heck could that be? You'll probably have the right idea. So it means objects which are microphysically thin and astronomically long. So we are interested in loops of string that are maybe a few light years in length. There would be lots of them in our galaxy and intergalactic space everywhere. And the thickness of them is some tiny, tiny subatomic diameter, depending on the energy scale at which these cosmic strings exist. So what are they made of? Well, there are two possibilities. One is they are defects from phase transitions early in the universe. So they're kind of like defects in a crystal. So a crystal, the simplest situation is to have a very uniform lattice of atoms, but there can be a defect. There could be a line of atoms that are missing. So you have your crystal, and there's a million atoms across over here, a million, but now there's a million minus one. So how did you get from a million here to one fewer here? Well, someplace there's like a hole, places that things don't line up. And the crystal has some extra energy in that place where things don't fit. And it is very much the same idea that would be here, only it's not crystals. It's not discretely spaced things. It's some kind of field theory. There's some way that at an early time in the universe, there's a symmetry breaking transition. The field goes from being uniform to being a little different in one place in the universe and another. And when the universe is cooled off, all the different ways in which it cooled off don't quite fit with each other. And so you end up with a narrow line going through space where things have not really cooled off and there's a high amount of energy there. So you could think of it as like a rubber band, something very thin, very springy. In fact, it's a sort of a relativistic rubber band. So when you pull on it, you put energy in, and that allows you to make more rubber, so to speak. So you can make it longer and longer as you go. So it doesn't have like a fixed length. A rubber band, you say, well, this rubber band is 3 inches long or something, but a string could have any length. When it's in a loop, it's oscillating, it's moving at some decent fraction of the speed of light as it moves around in some complicated periodic path. So you could imagine your rubber band again. Take the rubber band, stretch it out in some complicated shape, toss it up in the air, and it's going to go like this. Not at the speed of light, though. Cosmic string is going to go like this at half the speed of light, maybe. So that's what it is. Very massive, very rapidly moving. These are the ingredients we need for gravitational waves. So that's how these cosmic string loops could contribute to the formation of a gravitational wave background that we might be able to see.
Okay, I've got a number of questions. So you said that they're microscopically thin, astronomically long. I mean, effectively one-dimensional is what it sounds like. And are these observable potentially with the naked eye, or what sorts of radiation might they emit?
Right. So in the simplest case, the string, it's very thin. It doesn't have much effect on anything. It has very, very high energy, but the very high energy is confined into this very narrow tube. So, if we had this string in between us somewhere, we wouldn't be able to see much. In fact, they produce gravitational lensing. So there is a very, very tiny bending of light. If the light goes on one side of the string versus the other side of the string, it might be bent by a very small angle that would be hard to observe. Strings which were very, very massive. So I should say the string has an energy scale. So it could come from physics at various different energies. And the energy tells you the tension of the string, which is the same thing. It tells you how much energy there is in a certain length of string. And since we don't know what process it is that might be creating these strings, we don't know what that energy scale should be. But it can be limited. The higher it is, the more gravitational waves there will be, and the more effects of all kinds. So at the beginning, for example, people looked at the cosmic microwave background. They looked for an effect called the Kaiser-Stebbins effect, in which the temperature of the cosmic microwave background that we observe with satellites like Planck would be different on one side of the string and the other. So that would be a line. So you could imagine those cosmic microwave background pictures that we've all seen. And on the picture, there would be some kind of a line, maybe a wiggly line, with things a little bit hotter on one side and colder on the other side. So that would be a very clear effect. That requires a pretty high energy scale. And that was never seen. Strings of that scale would produce a huge background of gravitational waves, which we would also have seen. So NANOGrav is now the limiting observation. It sets the tightest upper limit on what the energy scale of cosmic strings could be. And so we know because of that, until you get into some even more exotic kind of strings, but the simplest kind of strings, which don't have ends, which come in loops or infinite strings, these strings would be seen in NANOGrav before you would see them in the microwave background. Or before you could see, for example, lensed galaxies. So there was a kind of a fuss a while back with the idea that there were two galaxies that looked very, very similar right next to each other. And maybe they were really one galaxy, and what we were seeing was two images of the same galaxy due to the lensing of a cosmic string. Well, eventually, they took a closer look at it with the Hubble Space Telescope, and it turned out just to be two galaxies that looked kind of the same. So that's another thing you could see, but we kind of knew that that was wrong at the time. I mean, it was very exciting, but we kind of also knew it was not likely to be really cosmic strings. And the reason is that the energy scale that would be required to have produced that gravitational lens was too high compared to other experiments, and it really was already ruled out. So that's the kind of things that we expect to look for. Now, cosmic strings may have cusps. A cusp is a place where the string forms itself up into something looking like this, moving very, very fast, nearly the speed of light in this direction. And it's possible that that could send out a beam of radiation here, making some sort of a flash. Again, we don't expect that because the dominating effect is different. And So the limits that are given by NANOGrav make that very unlikely, unless you go into more complicated models. There are lots of more complicated ideas, superconducting cosmic strings that could get electrical currents on them and then produce electromagnetic radiation from these cusps. They're kind of a wide range of possibilities.
Well, again, there are many things that I'd like to ask, but I think that the next thing that I should ask is what symmetry breaking transitions are, just because having a sense of why there might be cosmic strings in the first place might ground those further questions better.
All right, difficult to do with no visual aids here. So let me give a sort of an example. Suppose you have a bunch of, little needles or something, and they're all stuck in a lattice on a board. Okay, so here's this flat thing. You got these things that are all sticking up, okay? And they're all connected with little springs or rubber bands or something at the top. Under the force of gravity, they kind of all like to fall down. So they can all fall down the same way. Okay, everything is just fell to the left. They can fall to the right, towards you, towards me, whatever. But now suppose that all these things happened to fall down not in a uniform way. So these ones fell down like this, these ones fell down like that. So just look over here at the ones that fell down in this direction. Looks great. They're all falling down. They all fell down the same way. All the little springs that hold the tips together are fine. They're all happy. Look at the ones that fell the other way over here. They're happy too. But there's a problem. Because somewhere between the ones that fell this way and the ones that fell that way, there's some place in the middle. And these guys have a problem. Which way are they going to go? Well, they'd like to go this way to match those so that their springs would be happy. They'd like to go this way to match those. And you could say, well, okay, what about, if we make it into a curve? These are all falling down. These are falling down. These are falling down. Fine. But somewhere in the middle, one of these needles is standing up because it doesn't know which way to go. That's the symmetry break. At a symmetrical state, everything is up, same everywhere. We broke the symmetry by having them fall down. We broke it in different ways in different parts of the universe. Some fell one way, some fell the other way, and the result is a defect. There's a place where the thing didn't fall down. It's standing up, and now this one's standing up, and this one more and more and more are falling down, and these springs are all stretched out because these guys are pointing different ways, so there's energy there. This is a kind of a two-dimensional example of a type of symmetry breaking which would leave an unbroken symmetry behind with a little bit of energy left over, and we would call that a vortex. And if you just imagine a bunch of vortices stacked up, then that makes a string.
And what features of the early universe correspond to the strings and the needles and maybe even the plane in the example?
Right. So the plane just corresponds to space. The different parts of the plane, where some things fell one way and some the other way, those correspond to very far away parts of the universe that are out of causal contact with each other, meaning that there's no way for a signal traveling at less than the speed of light to have reached from one to the other. So when they decide to fall down, there's no way for them to coordinate. They can't say, let's all fall north, whatever that would mean in space. They can't all fall the same way because they aren't talking to each other, so they each have to pick randomly. And then later on, at a later time when more of the universe is in contact, it's revealed that they didn't all pick the same way. Now, what are the needles and the directions and so on? Those would be some field of physics, some new kind of particle that we don't know about, maybe associated with a grand unified theory. So if you take all the theories of physics that we have and you say these should all be somehow aspects of one theory, then everything has to be unified. There have to be new fields that take care of this unification for you. And in many cases, though not all cases, these fields will have the right properties to be like the needles that fall one way or another.
Granted that it's, of course, speculative, but are there any names floating around for what these fields might be, like the inflaton field or or other fields?
I don't think so. I mean, they might be the Higgs fields of grand unified symmetry breaking. So we have a Higgs field, and the corresponding particle was discovered not that long ago, which is responsible for a much more recent kind of symmetry breaking, the breaking of the electroweak symmetry. But if there's a grand unified theory, it would also have Higgs particles responsible for breaking it, and that those particles might be responsible also for making strings.
So moving on then, are there also possibly cosmic planes or cosmic solids, or is this just limited to strings?
Yes, no, it's not limited to strings. So you could have domain walls, which are like cosmic planes, where things are one way over here and another way over there, and there's some kind of a plane that separates the two parts of the universe where they're two different ways. You could have monopoles, which are cosmic points. Turns out all grand unified theories give rise to monopoles. And monopoles are a big problem because they form at early times, and then there are a lot of them, and there doesn't seem to be any way to get rid of them afterwards. So they sit around and would contribute a huge amount of energy to the universe that we don't see. So that is called the monopole problem. And the solution to the monopole problem is presumably inflation. Because if inflation comes along after these monopoles are formed, inflation takes some infinitesimal region of the universe and expands it into the entire universe that we can see. And so the monopoles are enormously diluted, so much that we wouldn't expect to be able to see even one. So now the problem is fixed. Cosmic strings don't have the monopole problem because they have another way to lose their energy, which is that the long strings cut each other up in pieces. So when two strings cross like this, they can get reconnected like this, so that you have one going this way, one going that way. So you have a string that comes around in a loop. It can touch itself here, reconnect. You now have a shorter long string and a loop. The loop is now going to oscillate. Gravitational waves get produced. Loop eventually vanishes because all its energy went into gravitational waves, and it's okay. So now we're not left with all the strings that we had way back in the Big Bang. The strings have managed to evaporate. So that's why strings are sort of a good, people are more interested in strings than anything else, I think, because they have some nice properties of this kind. Though people are interested in domain walls too, and there are some, many cases, domain walls can also behave in this way. And those are another possible source of gravitational waves.
So strings, monopoles, domain walls, if theoretically, and tell me if I'm wrong here, they all arise from symmetry breaking events, if we find one with this, like if we find a string, would this suddenly raise our credence that, oh, there must also be monopoles and domain walls? Or is it the case that if we confirm one, the others are still totally questionable?
Now, they come from different theories. I mean, the different properties of the symmetry that was broken. So you can have one but not the other. Now, as they say, monopoles, if you believe in grand unification, you always have. But you could have, for example, the formation of monopoles, then comes inflation, the monopoles are all diluted away to nothing, then come strings, and the strings are still here. So what it really would do, the important thing here is really more that we don't really have any idea about physics, fundamental physics at very high energy scales. So we know, what's going on in physics at the energies accessible to colliders. And then there's, who knows what comes after that? We can make educated guesses. If you found strings, and if we found them now, like if the next NANOGrav data set discovered strings, these strings would be at the level of 10 to the 13 or 10 to the 14 GeV. Those strings, that would be the first hint of physics at those energy scales. And then we would study them intensively and try to learn what was going on. The other thing which I started on the path toward but didn't mention is cosmic superstrings. So if string theory is right, the fundamental strings of string theory, the superstrings, could be stretched out by inflation to become of astronomical length. Those are a different thing. Those are not symmetry breaking strings. They're not made of anything. They're fundamental strings. They're what everything else is made of. Those would have different properties. Important different property they have is that this reconnection that I said, every time the strings cross, they're going to change partners and get reconnected. This would not happen all the time with superstrings. Depends on exactly the details of the theory, and I am not a string theorist. But people say that depending on the theory, the chance for them to reconnect with each other could be as low as 1 in 1,000. That string network would be different because of that low reconnection probability. So if you had that network with a low reconnection probability, you could distinguish it by some studies from the one with nearly reconnecting nearly all the time. And so you could identify that these are the strings of string theory. That would be fantastic because I don't know how long string theory has been being studied, 40 years maybe. And we still don't really have any clear confirmation. We have lots of theoretical reasons to think it might be right, but there's no observation. So this would be an observation of string theory in the sky, and everybody would be very excited.
Mm-hmm. Yeah, I think Ed Witten said that it would be very, very funny if after all this time string theory were confirmed by looking through a telescope rather than something else. But interesting. I had wanted to ask about the distinction between the first type of cosmic strings and cosmic superstrings, but maybe you just indicated this by saying you're not a string theorist. But by saying that you're not a string theorist, do you mean that you don't work on string theory, or you don't have high hopes that string theory is the final theory?
No, I just meant that I didn't work on it. And so you shouldn't ask me why the probability has to be at least 1 part in 1,000, because I wouldn't be able to answer you.
Okay. So do you have any hopes that string theory could be a final theory, or it's not something that you feel comfortable speculating about?
It could be right. It's frustrating. People have devoted their whole lives now to string theory. And most of the people that do it are convinced that it's right. I don't want to say that those people are wrong because it's not my field. I have no idea. It would be great. It's obviously a very rich theory with all kinds of things, which may be right. We are stymied because of this string theory landscape. So the great advantage of string theory is that string theory apparently is a single theory. There's only one string theory. There are no parameters. It's just what it is. All you have to do is figure out its consequences. Sadly, the consequences seem to be to generate an enormous number of universes, all of which have different properties. And so the dream of a while ago, which was to predict the properties of our universe from first principles, seems to be impossible. So the idea would be, like any other theory of physics, you understand the theory very carefully, you make predictions, you say, okay, this theory predicts this, this, and this, you go and look at for those things, and if you see them, you say, great, this correctly predicted all these properties of fundamental physics, must be right. Sadly, we're now in the situation where it can make lots of predictions, and we don't know for sure. And that's unfortunate, so I really don't know.
When you refer to the string theory landscape, are you referring to these 10 to the 500 ground states?
Yes, exactly.
Or so? And then I'm wondering, does string theory predict all of these universes, or is that just something that enters the picture with inflation and then maybe the anthropic principle? Because I'm not sure. I'm not as involved with this as you are, but I wasn't under the impression that all string theorists believe in the sort of like island multiverse conception where
So
there are all these.
string theory predicts that those possible low energy states exist. I mean, they are present as part of the theory. Whether they're populated is another question. That is to say, are there in fact parts of the universe or universes that have all those different 10 to the 500 or whatever, different possible low energy states and thus different possible laws of physics? That requires inflation. It requires eternal inflation, where inflation goes on forever, and then as inflation goes on, you can have tunneling events that get you from any place in the landscape maybe to some adjacent place in the landscape, and so on until you've produced a populated landscape with a different region of the universe or different universe in every one of those things, most of which, of course, disappear in a tiny fraction of a second, but presumably there are in this 10 to the 500, which is a huge number, many, many, many long-lived possibilities to make universes which are somewhat like ours. And we maybe live in one of those.
Okay, now that we're getting into distinctions between existence and population, things are quickly becoming philosophical, which might sidetrack us a little bit. But just to be clear, when you say that these 10 to the 500 ground states exist in the theory, you mean that there are, I'm wondering if you mean that there are potential models of the theory in which any one of these ground states is instantiated, or you mean that there must be a physically extant string in one of these ground
Exists
states?
is probably the poor choice of words, though I don't know a better one. What I mean is that the theory predicts that those things are possible.
Okay, great. That's what I wanted to clarify. Okay, and then now going back a little bit, you said earlier, restricting ourselves now to the first type of cosmic string, not the cosmic superstring, but you said that they don't, aside from the gravitational lensing, they don't have, and of course the propagation of gravitational waves, they don't have much of an effect on anything, because beyond being highly massive and energetic, they're, you said, confined to a narrow tube. And I was wondering what is doing the confining, or if in this like very exotic case, it's just the best word, but there isn't actually a confining material or substance.
So what's doing the confining is, you could go back to this example I tried to give about needles. The inside the core of the string, the symmetry is unbroken, and you're in an extremely high energy state. So the universe does not want, so to speak, to have any more of this high energy state than necessary. So if you had a very wide string, so why don't I have a string which is 1 millimeter wide? Well, that would have a huge amount of energy. It could lose its energy by shrinking. It could not lose its energy by shrinking away to nothing. So it shrinks and it shrinks and it shrinks, losing energy, searching always for a lower energy state until it gets to some critical size where it cannot shrink anymore. And the reason it can't shrink is that not only is there energy associated with being at each individual point in this high energy state, but there's energy associated with changing rapidly from one place to another. We call it gradient energy. This is like the energy that I imagine to be in these little springs that connect the tip of my needles. So there's a point at which those things cancel, I mean, the attempt to get lower energy by shrinking is now canceled out by the fact that you get even higher energy by changing the rate of difference between the field in one place and a field nearby, and then the shrinking stops. So there's an equilibrium size, and that size is determined by the energy scale. Higher the energy, the smaller the string is, the thinner the string is, but the more massive it is per unit length. So that's the process that leads to this confinement.
So another thing you said, so they're very massive and they're rapidly moving, and I understand the very massive part because they're highly energetic, but what is it that causes their acceleration? So with the supermassive black holes, it's another supermassive black hole and they spiral around each other. That's what causes the acceleration. But why is it that all, or maybe you didn't say all cosmic strings, but why would cosmic strings be moving so quickly?
Well, in principle, you can have an infinitely long straight cosmic string and it's not moving at all. But in the real world, the strings are not straight and the strings have tension. So, if you take your rubber band and you stretch it out straight, well, okay, it's going to sit there. But if you put it in a not straight configuration, force it into that configuration and let go, then it's going to start moving around. And it's just that. The string tension always pulls on the string, so every place that it's curved, it tries to pull that curve inward. Because the tension is so high compared to the mass of the string, this is what makes them relativistic strings. So there is a sort of natural speed, and the natural speed is a big fraction of the speed of light. And that has to do with comparing the tension to the mass. So if you take a guitar and you tighten up the tension on the string, then the string makes a higher note because the mass of the string is the same, but now it's under more tension. You want to have a low note coming from your guitar, then you make it out of a massive guitar string. It's thick. And now it is going to move more slowly because the tension is not so large compared to the mass. Well, here we're at a very extreme limit where the tension is in relativistic units the same as the mass density. And so that causes the thing to move at about the speed of light, some fraction of the speed of light. So, of course, a loop can never be straight. Because if it were straight, it wouldn't be a loop. It has to loop back on itself. So the simplest case you could imagine would be exactly circular loop. It's just in a circle. You create it here by hand. And now, because of symmetry, this thing would just shrink exactly down into nothing. And the whole thing would evaporate. But in the real world, things are not perfect circles. So the string that you would really see in the real world is formed of a loop, which is full of all kind of complicated wiggles. So instead of having a loop like this, you would have some complicated thing. The complicated thing would not collide with itself. It would just go in some periodic motion at half the speed of light or something, and then it would do that forever if it weren't for gravitational waves, and because of gravitational waves, it shrinks very slowly. So maybe after 10 billion of these oscillations, it's evaporated away.
This is all like pretty mind-blowing. I'm really enjoying this. Now, how would all of this be parsed by the NANOGrav data? I also imagine that, the supermassive black holes, they're not effectively one-dimensional. They're three-dimensional, and we know where to look for them, which makes them a lot easier to find. And they're not, they're rapidly moving, but in a predetermined pattern of sort. Whereas the strings are none of these things. They're one-dimensional. They're not, as far as I can tell, they're not moving in the sort of circular pattern or elliptical pattern that a supermassive black hole would be moving in. And we don't know where to look for them. So how does all of this factor into parsing the data to determine whether or not cosmic strings are contributing to the gravitational wave background?
Right. So what we need to do, so we don't have that much information about the gravitational wave background that we're observing. one thing that we know is something about the spectrum. So you can say, what spectrum would it have if it were produced by gravitational waves from black holes? What spectrum would it have if we're observing gravitational waves from cosmic strings? Neither of these things is very easy to compute. In fact, in a certain sense, the cosmic string one is easier. So what we do, and I've been doing this now for quite a long time, is we simulate a cosmic string network. So there's no theory that you can just put in that was going to get the answer out by a calculation on paper. We simulate a cosmic string network. We see it with long strings moving around. We see them crossing each other, crossing themselves, producing loops. We write down the shape of those loops. Then we simulate each loop again. We simulate it moving around, oscillating in a periodic way, losing energy due to gravitational waves, which we also calculate. We see how it changes its shape during its lifetime. Then we gather all this information. We do a cosmological calculation. We say, okay, so from the simulation, we figure out how many loops there are of all different sizes, what we should expect in our universe. Big loops, little loops, how many of each are there? Then for each loop, we say what possible range of shapes can it have. So we have hundreds of loops that we got from simulations representing lots of different shapes. For each shape, we figure out what gravitational wave spectrum it has and also how the shape changes over time. And then we just put together all these things. We add them up over all the different shapes of loops, all the different eras of the universe, all the different places the loops might be. And when we're all done, we have a spectrum. So that's been my business for a while. And now we compare the spectrum against what we see in NANOGrav. Similarly, the people that study the black holes try to do the same thing. How many galaxies are there in the universe? How big is the black hole in each galaxy? How often do they merge? What do the black holes do when they merge? All these things, and they try to find out what would be the spectrum of black holes, of gravitational waves coming from black holes. Now we compare. Does the spectrum look like, that we see, does the spectrum look like what you would expect from black holes? Unfortunately, there's a great deal of uncertainty about what is going on at centers of galaxies. So we don't really know for sure what the spectrum of black holes should be. The best guess we have, it looks okay, but not great. There is some tension between the spectrum as we see by NANOGrav and what you would expect from black holes. Now, you shouldn't be very alarmed about that because our ability to determine the spectrum is not that great. After all, we've only just gotten believable evidence that the thing exists at all, so we can't know too much about its properties. So we aren't sure of the spectrum. We aren't that sure of the spectrum from black holes. There is a sort of a mild tension. Maybe they don't look so good. Now you can say, what is the spectrum from cosmic strings? Well, that we're actually more sure of, except that what is the energy scale of the cosmic strings? What is their tension, their energy density per length? We don't know because they're coming from some theory. We don't know what the theory is. So there's an uncertainty. So now you try to fit these things together and you say, do the cosmic strings fit well with the data from NANOGrav? And the answer to that is not very well. So this particular model, the simplest model of cosmic strings, not superstrings, nothing complicated, cosmic strings that are topological defects, does not do a good job of explaining the NANOGrav data. The spectrum does not really have the right shape. When you make the amplitude, so there's one parameter, it's basically two things to explain. One is the spectrum and one is the amplitude. And it turns out, and we have one parameter to adjust, which is the energy density in the string. If you adjust it to make the amplitude right, the spectrum doesn't look so good. If you go to superstrings, they look great. Why do they look great? Because now there are two parameters. There's the reconnection probability and also the energy scale. So of course, with two parameters, it's a lot easier to fit something. So the answer is we don't know. There's just no way to say. And as I say, if you wanted to put money on what is the source of the cosmic of the gravitational waves observed by NANOGrav, you should put your money on black hole binaries, because we know that black holes exist and we know that galaxies merge. But what instead we should be doing is not betting, but trying to get more data, do better analysis, more pulsars, longer times of observations, better analysis codes, to try to figure out what it really is coming from.
Before I dig into all of that, one phrase you used a few times is the cosmic string network. Is this something beyond, and I started saying beyond and above at the same time, something beyond and above just the totality of cosmic strings that there might be?
No, it just means all the strings in the universe. They're not exactly a network, because what there are is infinitely long strings, maybe, that just go on forever through the universe, and loops. So you won't catch fish in this net, because a fish net needs to have vertices where more than one string is attached. Otherwise, the fish can escape. Nevertheless, we call it a network.
So you said that, I think that this is what you said, that neither the super black hole mergers is a perfect mesh with the data, and neither the cosmic string spectra is a perfect match with the data. Combined, do they match much better with the data, or is it still not quite a fit?
So regular cosmic strings, not superstrings, nothing special, we don't help fit the data. So you can add them in, and it will not make much improvement to the fit with the data. All the other things that we've tried do help fit the data. So you can have cosmic superstrings plus black holes. Since we know black holes exist, this is, of course, the thing we should be looking for. Black holes plus some other source. And so, we have a paper, and the paper has a bunch of factors by which these things fit better. And for many of these sources, the factor is between 10 and 100. Looks 10 times more likely, 10 times better fit. But it doesn't mean anything, because this is just dependent on our guesses, basically, about what the black hole spectrum should look like, what possibilities you want to consider. If you consider lots and lots of possibilities for strings, let's say, then they don't look very good, because many of the possibilities are no good. If you consider just a very narrow range of possible energies, for example, that happens to be around the right one, then of course it looks better. So there's just no way to know besides waiting for better data and analysis.
Mm-hmm. Well, beyond the supermassive black holes, then the cosmic superstrings, the cosmic strings, monopoles, boundaries, are there any other possible sources, exotic or otherwise, of the gravitational wave background that we know of? Certainly, there are possibilities that we don't know of and haven't conjectured, but that we have conjectured.
There are many possibilities. In the NANOGrav New Physics paper, we studied the ones that we had people in our collaboration that had the knowledge to study them. So we studied gravitational waves directly from inflation. We studied gravitational waves from the inhomogeneities that occur from inflation. So maybe inflation would produce some black holes. Now, it takes some sort of non-standard version of inflation to do this, but inflation would produce some black holes. The black holes would move around for a while, produce gravitational waves. We studied, what else? Phase transitions. So, we know there was a series of phase transitions early in the universe, and it's possible that one of them proceeded in a way that involved the nucleation of bubbles. So, like if you boil water on your stove, that's a phase transition, and it produces bubbles of steam. Well, if there were bubbles of different materials early in the universe, the bubbles would collide with each other. Again, very massive objects moving around very rapidly. That could produce gravitational waves. And the universe is always transparent to gravitational waves. So anything produced, no matter how early, at the beginning of the Big Bang would still be around. So we studied a whole list of these things. Maybe that's all of them, or maybe I've forgotten some. I'm not sure.
Well, the last thing that I would like to ask for today goes back to something you said offhandedly earlier when we were talking. I think it was when we were talking about the ground states of string theory and the multiverse, or it might have been before that even. But you mentioned that it's theoretically possible to move from, say, one island universe to another in the multiverse. And for those of our listeners who haven't heard of the island multiverse before, it is so massive. I mean, it's there could be a potential infinite number of universes in the multiverse. So I'm just wondering what the mechanism is by which this travel would occur.
So I did not mean to say that you could travel from one part of the multiverse to another. What can happen is that when let's say you're in a particular one of the 10 to the 500 vacua of string theory, and you're inflating. So you're in a piece of inflating universe. It is possible for a bubble of a different possible one of the 10 to the 500 vacua to appear inside your inflating universe. So it could appear around you. I mean, like, nobody could live in this type of a world, but, just imagine you're a point in that universe, then a new kind of inflating universe with different physics could appear around you. And another one could appear yet around you, or another one could appear next to you, and then inflation would rapidly carry it off, and it would be very, very far away. You wouldn't be able to reach it. So what I meant by moving from one place to another, it was only changes in which of these 10 to the 500 states some particular point is in. After things have cooled down, then it becomes wildly unlikely for anything more to happen. So it's not likely that the universe that we're in is going to suddenly turn into some other state of string theory.
Well, then I'll ask more particularly, is there any theoretical reason why a wormhole like an Einstein-Rosen bridge couldn't connect to island universes?
Well, there are two questions here. One is whether wormholes can exist, and the other the other is whether there's some reason for them to form. So wormholes can only exist if you violate the average null energy condition. This is a subject for a different episode, maybe. But I showed with my student that in quantum field theory, given a bunch of particular assumptions, you cannot violate this condition, and therefore you cannot have a wormhole, or you could have a wormhole that maybe existed momentarily, but you can't travel through it. So wormholes do not seem likely, and it would require some sort of new physics that we don't know anything about. And also, even if there were wormholes, why would there be a wormhole connecting our universe with some other one? I mean, of course, it's great for writing science fiction stories, but where would it come from? The universe is expanding at a prodigious rate in the middle of inflation. What process would it be that produces the wormhole that somehow connects two of these things? So I don't know of one. So even apart from the question of whether the wormhole could exist, it seems unlikely that they would ever be produced.
Okay. Well, Ken, thank you so much for humoring all of my questions. This has been a lot of fun, and I really appreciate your taking the time to talk with me today. Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Erhardt.